All right, so we are going to continue with our Python fundamentals, and we're going to finish today, I hope, dealing with how to define larger arrays or arrays both in 1D and 2D, meaning vectors and matrices of any size, and not just typing in our 3x3 matrices, which are simple to type in, right? Those continue to be nice and simple problems we can look at entirely. But in practice, in general, we're going to be interested in very large vectors and very large arrays. So before we do that, I'm going to introduce one more tool that is going to be specifically useful for homework. And I'm going to exemplify why. So this is called Jupyter Notebook. So this is another environment. So Python underneath is still the same Python we've been dealing with. But it's actually connecting to Python, but it can really connect through this web browser to really any other program. The whole point of Jupyter Notebook is to create this web-based environment that can call anything behind the scene and display the result within a web browser. And the key point for that is that web browser, we all have web browsers. You have web browser on your phone. Okay? So that makes it simpler to interface sometimes with complex things, and you can basically, that complex environment that you're connecting to could be on some remote computer, not yours, but you basically interface the web browser. So that is kind of what you're doing at the moment you're logging into a Facebook account, right? All of the computation, everything that Facebook is searching for, tagging, working on, and there's a whole lot of work behind in figuring out similarities between your friends and finding their faces in your photographs, okay? There's a lot of computation going behind. That computation is not done on your phone. That computation is done elsewhere. And you're just kind of connecting to the display result of all of that communication or computation through your web browser. So Jupyter Notebook is one such environment for sort of like programmers. Okay? And what's neat about it is that both the code, any comments in the code, including highly formatted text, not just text, but like formatted text, type of like anything that you could find on a web page, is juxtaposed in parallel with the results. So results are kind of embedded into it, and you can easily sort of save it as a document. In this case, it's going to be your homework, right? And you don't have to grab individual things and cut, copy, to paste them to a separate file. So that should streamline the way you do homework. So let's, without me talking about it, open Anaconda Navigator. And instead of Spider still works, by the way. It's just that this is an alternative way that I think is going to speed you up in terms of submitting homework. So open Jupyter Notebook and just say launch. And you will see something, probably, maybe not, pop up in your terminal. This is sort of the back end. This is the business end that I'm just going to minimize and forget about. But actually, it's telling you what it did. So my computer is a wireless network. This is its name. I'm user Masha. And when it started, it gave me the command that it started. And it's actually anaconda3/bin/jupyter_mac.command. So that's simply the command that got executed. You don't have to think about it, but that's kind of like sitting in the background. And any kind of things that it's doing in the background, if you're interested, you can see in this window. Okay? So whatever you actually work from web browser, you can see a little bit of a log of it here. Again, not important here. I'm just going to forget about it. This is just if you're interested. So what opened now, I hope, is another tab in your web browser, just along with I had email open, and I had my Digital Rocks portal open. And my third tab, I have now a new tab in my web browser. Okay. And the web browser that is going to be called is whatever default web browser is on your computer, if you have multiple. And what I see right now, this is my local directory, the root for me as a user. So now you go to whatever folder that you keep files in. Okay? So if you have a folder for this course, you walk yourself to it. So you use this just like you would any kind of selection of folders. So I'm going to go to mine, 310, and then I'm going to go to lectures. Oh, and this is where my Python scripts are. And I've uploaded already scripts that I'm going to use here. But I'm actually going to create, so these are the scripts that are already available. These notebook scripts are I, P, Y, and B. Okay, so that is a specific format for notebook. It can read in your Python files, just .py, just fine. But there's more to it than just Python, so these are called I, P, Y, and B. So I'm going to right now actually just kind of open a new one. It doesn't matter. I can open the ones that I prepared for you, or I can just go to, and you can see here files. So if I'm just going to show what I mean in one of them. So this is plotting that we're going to work on a little later. Okay. So you can see this is a code. This is the same code that I would type into my Spider or any Python environment. And this is the result immediately executed afterwards. Okay. And if you actually just for practice want to open, I can actually download this and you can download it as a notebook, which is file that works in Jupyter or can be written in Jupyter. You can download, you can strip this code of any known code and download it as a Python that you can open in Spider. Or if I was submitting homework, it can be HTML, so you can post it on your website. Okay? Or it can actually be, there is for editing, I'm interested in PDF. Okay? So if I download PDF, it's working on it. Behind, it's actually producing PDF on my computer. And once it's done, it's going to let me know. It's going to ask me, hey, do you want to open it? Preview is a PDF viewer on my computer, or do you want to save it? You can do either. Let me open it just to quickly see it. So these are all of the actually plots from that file together with the code, right? So you can see how is this useful for your homework, okay? So you're going to produce this PDF and just print it out and you'll be done. Yes? Yes?
Do we have to be the owner of the file for it to work, or
No,
no?
it should be downloaded somewhere on your phone, on your computer, I'm sorry.
If I download it from Canvas into my own files, and then I just download it as a PDF and I get a 500 internal server error?
Yes, so you don't open that PDF in Jupyter.
Okay.
That's just for printing it out later. So in Jupyter, you open there's I, P, Y, and B files that I posted in the code. So that's what you open. Okay? Do you still have trouble with that?
Yeah, so if I went to the same spot you did to download it as a PDF?
Mm-hmm. Not as a PDF. It should be downloaded as is. Okay? So in Canvas,
I was able to download it from Canvas and it's on my computer, but when I went to that exact spot you were just at, I'm not able to download it as a PDF.
Precisely, you have to open it inside of this as IPYNB, okay? And then you say save as PDF.
Yeah, and I can't save it as a PDF. I get an internal server error.
Okay, I'm gonna be there in a second. Does anybody else have a problem with that?
Oh, everybody? Everybody?
All right. Okay, so there is XC. So can you just email me this error? Okay. So there is a LaTeX problem. it looks like that it needs extra software layer to do that. And you're gonna send me, and I'm gonna find how you do that. That's somehow miraculously already installed on my computer. Okay. So let's now, for now, we can just work with, you can try downloading HTML or something, but we're gonna fix that later. Or you'll be able to just submit this IPYNB. We can print from just here. So if you open this Lecture 2.5 plots, okay, you see this? Can you just print from Firefox or whatever is your web browser and save into a PDF for now? All right, just got that one. Can you try that? So print command from your browser. And then print into a PDF instead of printing to a printer. And see whether that works. So that can be a workaround until you install something else. Okay? All right, that works. So you have a workaround, but email me the error and I'm going to send you what to do. All right. So this is just to show you what can happen. Okay? And what we have, I'm actually gonna now just open a new notebook in Python 3. And that's where we're gonna be typing things in. If you're in a lazy mode today, when I do share these files with you, you can just go and actually click on this particular cell. And you can say Shift Return or Shift Enter. And it's going to execute again. And sometimes it does need twice. Okay? So you Shift Enter or Shift Return, depending on which machine you have. And that's going to execute this cell again. Otherwise, what you're looking at is what executed on my computer, and it's just shared with you. So when you really have a bad day and don't want to type, this is one way to still tag along with the lecture. However, if you just kind of execute this and you don't read through what's in there, that's kind of dangerous because it gives you a feeling that you know something and you don't really know what to type in. Okay? So you do want to actually type along with me. Okay? But again, for here and there, if you're trying to catch up, you can still do this. But we're going to actually do a new one, okay? And I have a little review exercise as this quick recap. So I want you to try this out. In this cell that is opened in this new file that you have on Jupyter Notebooks. First, I want you to try in the first cell is, can we define a variable named a minus h and assign it a value 5? Give it a try. You might already know the answer. No, do that in a new one. Just do a new one, not to mess the other one up. So a minus h is equal to 5. Yes? Now when I press enter, nothing will happen. This is not a command line. I will try. I don't know how, actually. So try Firefox preferences. A minus h, can you define something? Okay. Like it's not catching on for some reason.
Top corner to increase the percentage to like 120 or something at the top, like the little thing.
Here?
Use like 120%.
For the Zoom.
All right. Hey, we'll see how figures will look like with this, but for now this is good. Eh? So, and if I press enter or return, nothing will happen, okay? For this cell to actually know that you are done typing and you want to execute what's typed in, you have to do shift return. So shift return or shift enter. Shift return, shift enter. And here it's gonna let me know, hey, you have a syntax problem here. Okay. You can't assign to operators. So basically what it's confused about is this minus. It shouldn't be part of a name of a variable. Okay. Now I can fix this up and just call my variable AH or something. And again, so now I fixed it up. And again, shift return or shift enter. And now it's actually fine. I don't have variable explorer here. But in order to figure out, hey, did it assign things correctly? I can again print AH. Just to see, hey, is that AH that I like? And yes, it is. It executed and it gave me the result right underneath. How I organize my life in these cells is up to me. I could have actually just said in this new cell, hey, well, print it here. Print AH plus 7. Okay. So it's my logical pieces that these cells are. Computer has nothing to do with how you break it up. And for some reason, for me, this new one. So information from one cell to the other does travel, right? So as long as at the beginning of your file you execute something, it should be traveling. Here and there you'll have to redo it if it kind of gets stale or you go away or something like that. Okay, so I can work with it just like, and my results are right in there. So let's actually now go to the rest of this is basically a recap of what we've been doing, but we are going to do this in Jupyter instead of Spider. So I know that for two scalars, if I have alpha times beta, it's the same as beta times alpha. We kind of already know that that's not true for matrices, but I'd like to check that here. So I want you to create two matrices, A and B, using those numpy commands to create arrays. And I want them to be size 3 by 3. And I want you to check, hey, is A times B the same as B times A? And then we'll actually do a little bit of the same thing with the vector. So I'm gonna leave you for a second. One thing that I'm gonna say here, so I'm gonna create a new cell because this is now logically a new session. One thing that you always have to do is say import numpy as np. Okay? Before you can call numpy commands. So this executed fine, but I'm going to go back to that cell and continue writing. But you can execute it just to check, hey, is this fine? So give me a color. Blue. All right. Blue shirts, starting from the top. Who is the first blue shirt? You have a blue striped shirt. That works. Blue striped shirt. So how do I define a 3 by 3 matrix? What's the command in NumPy that I use? np.array. Cool. So now I need the first row. Just give me 3 numbers. 12, 1, 0. Okay, that's my first row. Next blue shirt. Give me a second row. 2, 5, 7. Give me the third row too. 5, 4, 8. Okay, so I go row by row, and every row is in its separate angular brackets. And I'm gonna do print A just to see that I did things right. And shift return or shift enter executes the cell. And my result appears right here. So I don't know how about you, but it is easier for me to see the result immediately below as opposed to Spider, where it's sometimes, if you're recording it, it's in a separate file, and that file is an editor, and you're in command line, yes?
What's the purpose of the semicolon?
None, really. This is my programming habit. It can be, it doesn't have to be there. Let's see, actually. Yeah, it's a programming, in other languages, you put it at the end. And here it doesn't do much. All right, so now I need matrix B. What's my next blue shirt? We have more striped blue shirts. Look at that. All right. I didn't get the memo that I had to do a striped blue shirt today. All right. So also NP array. So give me first row.
3, 4, 5.
3, 4, 5. Don't forget the commas. I always forget them. And then I need the second row.
2, 1, 0.
2, 1, 0. And one more, and then we're done.
11, 15, 12.
Awesome. And I'm gonna just print B instead now, just to check that I did it right. So when I change the code, I do shift enter to redo it, and it kind of changes it in place. Who is next in blue? How do I multiply them? There's a command. No, print just prints it out, but I want to multiply. So this is my NP command. MATMUL, matrix multiplication. Okay? A, B. Now, if I wanted to store this in a matrix C, what would I have to write? C equals. So I'm going to remember it because I want to do something with it. Cool. And then I'm going to call the other one D, which is NP, the same thing, but B, comma, A. Oops, wrong A. Uppercase, lowercase, it is different. So it executed without complaining. I could print C and D and see whether they're the same to check whether A times B is the same as B times A. I could also do a little more math and simply print the difference. And if they're the same, then difference better be 0. If they're not the same, well, the difference is not 0. Ready? Moment of truth. Not that they're different, they're really different. Okay? So A times B is not the same as B times A in the matrix world. Who is my next blue? Blues, is that blue? I'm going to call that blue. Blue, kind of blue, grayish kind of blue. All right. So let's now define a vector x. What is the shape of a vector x so that I can multiply A times x? Three by 1. That is correct. Now, what did we say about Python? So how do I define just a 1D array? I'm going to call it X. I could use the same command. That would be its dimension, yes. But if I want to just define it, give me 3 numbers.
5, 8.
5, 8. One more? 9. Awesome. All right. So this is now a 1D array, okay? And I'm gonna check its shape, by the way. So I can check shape of both by saying a.shape and x.shape, if you remember from last time. You probably don't, but that's all right. That's why we're reviewing this. So by the way, when I ask you questions like this, you don't know the answer, it doesn't matter. The point is to kind of get everybody's memory going. I don't remember who knew what and who didn't. If you ask me a day after, I'd be like, say what? Okay? There's too much that happens in one day for me to remember anything. Okay? So now, I'm actually, who is my next blue? Blue suit. Oh, with blue tie. Nice matching tie. Good job. So how do I comment this if I don't want it to show up?
Hashtag.
Hashtag. We'll just comment it out so it's not going to get printed. Now, for some reason, it doesn't print the shape of A. That's hilarious. Okay. So shape of A is 3 by 3. Shape of X is 3 nothing, so it's 1D array. So let's do the same thing. I'm going to give it a vector Y. Is how do I multiply the two? Next blue, that's kind of dark blue.
Yes.
Multiply.
A and X, yeah. Math, move. All right, A and X. And I'm gonna call this Y1, Y2. I'm gonna do the same thing with X comma A. So try to multiply a vector with a matrix. And let's execute. So it both it didn't complain. It means it did something. I can print Y1 and print Y2 and execute again just to get them. And in both cases, it actually performed the multiplication. So just to jostle your memory, when I define a 1D array, and I try to multiply it with a matrix, it's going to interpret it either as a row or a column vector and perform the operation. So if I'm trying to multiply matrix times a vector, 3 by 3 matrix times a vector, I need a 3 by 1 vector. So this 1D array is going to be interpreted as a 3 by 1 vector, even though it doesn't really have that second dimension. It just has 3 elements. And if I'm trying to do X times A, what should be the dimension of my vector to be able to do that matrix multiplication? A is 3 by 3. My vector should be, to do this one, 1 by 3, so it should be a row vector. So basically, in this case, in the second case, it's going to interpret my vector as a row vector. It doesn't care, as long as you have enough elements. Okay. So that's what it does with 1D vectors. And that's just Python implementation. Somebody decided to go with it because it was simpler in their role. Okay, whatever it is that they were implementing. And this points out, so somebody asked the question just before this about the dot product. So dot product expects these 1D arrays, not matrices. It's not going to convert matrix for you. But you can always force the shape to be a vector. So if I wanted to change the shape of A, And this is actually our last thing, change the shape of A into a 9 by 1. I do have 9 numbers. So if you remember, print A, I'm actually going to do that in a separate thing. So I'm going to print A, and then I'm going to say, tell me what shape A is. And then I'm going to force that shape to be something else. And I'm going to say 9, 1. And I'm going to print A again, just to see what it did. Is everybody following? Am I speaking Croatian? Speaking Python, speaking Croatian, same thing? In terms of level of understanding? Alright, so let's execute this just to see what it does. So this was my A, okay? And for some reason it refuses to print A.shape. Okay, we're gonna force it to print. And execute again. And when you force it to, oh, now it already changed it. Ah. So now it already executed it a couple of times, so I'm gonna force first 3 by 3 or back, okay? So this is my 3 by 3 shape, and it printed both A and its shape. So here and there, so for instance in Python environment, we could just type in A.shape and it would print. Here and there, sometimes because it's translating things to the web browser doesn't catch it necessarily. So you have to force it by saying print.
So for the dot product, we use this, and not. I looked online and there's something called np.dot. We don't use that. We don't use np.dot.
No, we use dot. np dot.
We do use that.
Yeah. Okay. That's what we introduced. This? So basically now it took first row, okay, it created 9 by 1, and it just took, it basically goes down the rows and grabs values and just fills whatever matrix you wanted to fill. So it took 12, 1, 0, 2, 5, 7 and just arranged it in a 9 by 1. 12, 1, 0, 2, 5, 7, 5, 7, 5, 4, 8. Okay? So it just goes down rows and just fills in what it needs to. And it changed the shape. So if you defined initially your vectors as actually matrices that are like 3 by 1 and have that, you can force the dimension to be 3, so here I could have actually put, this would be forcing it to be 1D array, okay? And then when it's 1D array, then it's always printed as a row. 1D arrays are just printed as rows always. Okay? So this is just 1D array, 9, 1 is actually a 2D array, or rather my numbers forced into a 2-dimensional array. And this is each row, okay? Okay, questions? All right, so this was review. Now we will actually go back to what we started working with. So last time we introduced linspace, arange, and logspace. This is one way to get 1D arrays that kind of can have any number of elements. So what linspace does, it really goes between 1 and 100. These are the limits, start and end, and how many points you want in between equally spaced. This is just to give you a quick number. And 10 is easy, but when you want 100, you definitely don't want to type that in. Okay? Arange does pretty much the same thing, but what you're defining here is the step size. So make them spaced 11, yes.
Are we going to stay in Jupyter doing this, or are we going to switch back to
Just
Python?
let's keep in Jupyter. Yeah. If you want to retype this now, you can, but we're going to have examples of this when we start plotting, so there is no need to retype. I'm just reviewing what we did last time. Okay. And then logspace does kind of, let's just do this logspace business just to see what it does, because I think I did it briefly at the end. So x is np logspace 133, and I'm going to print x. So it works in log 10 space. So between 10 to the 1 and 10 to the 3, it's giving you 3 equally spaced points, equally spaced in log space. So log of it is equally spaced. So logarithms, or the exponents that are equally spaced in this case, are 1, 2, and 3. So what you're getting is 10 to the 1, 10 to the 2, and 10 to the 3. Okay. Again, sometimes we need that because, quite frankly, most of the properties in petroleum engineering go over multiple orders of magnitude in length, for instance. Your reservoir is in kilometers, your pore spaces are in microns. 10 to the minus 6 versus 10 to the 3. If you're going to plot all of whatever it is that you're measuring over the entire space of that, you've got to use log of length, or else you won't see anything not on the same plot anyway. Does that make sense? If I'm plotting lengths, let's say that I'm measuring fracture apertures. That's the spacing of a fracture, right? And they actually do run from microns all the way to meters plus, okay? So that's from 10 to the minus 6 meters to 10 meters, say. Okay? If I'm going to plot that on the same plot, it doesn't fit into the same length like that you can get a meaningful plot. So you've got to do log of that length in order to actually show something. So as an engineer, you always kind of have to do log spaces, so this is why I have to introduce this. Okay.
Each one of those numbers represent 1, 3, and 3.
So these are exponents of 10 potential. So basically 10 to the 1 is 10, 10 to the 2, 10 to the 3. So 1, 2, 3 is equal spacing in this log space, log of these numbers. Log of these numbers are 1, 2, and 3. They're equally spaced. We could do 4 here, but then the numbers wouldn't run so pretty. You would still end up with 1,000, which is 10 to the 3. But these don't look as pretty, but they're equally spaced in log space.
So the middle number is the highest power. So you use that.
The powers over exponentials.
The last number is how many spaces you want.
Starting power, ending power, and how many in between. That are equally spaced in log of the numbers. Okie doke. Moving on. So let's now do some random numbers. So these are another 5 functions that we're going to use often to just create some random arrays when we don't know what the numbers should be. Our identity. Identity really just gives me identity matrix. Then there's rand function that is in the special space called the np random. And then np diagonal, zeros, and ones. So let's try this one. What does np? I'm gonna retype it. np random, rand of 4 times 2. So 4 by 2 is my dimension. And what I'm going to get as a result is a matrix, 4 by 2 matrix, that gives me random numbers between 0 and 1. And I'm going to print it, otherwise I'm not going to see it. So if I execute that, I get indeed 4 by 2, and all of these numbers are in between 0 and 1. So this is the basic algorithm just to get some output that I can work with. What I really know about my reservoir is that in certain block, my measured porosity, I know I have a sandstone, I know roughly the porosity of that sandstone. So I know kind of that I have, for instance, porosities or permeabilities in certain range. So I will want to scale this, okay? Porosities are fine. They actually run between 0 and 1 in general. So 0 and 1 is mathematically the range of porosities, but in reality, my porosities are between 0.1 and 0.3, right? So if you want to scale this in any way, you can just do mathematical operations with it. So what I'm going to do, and I'm going to work in that same cell, I'm going to just do random operation of 5 plus 5 times r. That will start with 5, and then it will add, my r's are between 0 and 1. So I'm going to add to 5. 5 is simply translating in things, numbers that are between 0 and 5. So I'm going to get a range that is between 5 and 10 as a result. Right? So let's test that that's indeed the case. Whoops, it printed both. So these are my r's, because that's how I printed it. And these are my actually 5 plus 5 times r's. So I have numbers indeed between 5 and 10. Yes?
Is your R always going to be the same even though it's random?
No, that's a great point. So let's remember this first number, right? 0.0. So every time I execute, I can get a different result because it's a random. Now, what I can set is, I believe, np random.seed and just give it a number. Let's try with 1, 2, 3, 4, 5. If not, that should fix it to a fixed seed. And now, whoops, every time I execute, I should get the, so let's fix on this number. Let's see whether it's the same. No, maybe it has to be, I had a seed function. Maybe it just needs to be a larger number. Yeah, so it has to have 8 digits, this seed. So this fixes rand to always execute the same. Otherwise, it's just gonna, it's like rolling a dice, okay? And if you don't have it, then you're gonna get a different result every time. So again, seed should have 8 digits. Let's create a diagonal matrix. I'm going to call it D, NP diag. And I'm going to just, so what it does is it takes whatever vector I give it and creates the matrix that has those same values on a diagonal and 0 otherwise. So I'm going to be my inventive self as usual and do 1, 2, 3. And I don't know anything until I print it. So I say print D and shift enter, shift return. So my D is my diagonal matrix with these numbers 1, 2, 3 as a diagonal. I can do zeros. Let's call it zeros. O's. O's is np dot zeros. So I'm just trying all of these here. Zeros, and I'm gonna give it dimension 4 by 4. Oops. No, it doesn't like 4, 4. And
print. Oh. I think zeros in a different dimension wants this.
So the reason why it actually wants me to put this curvy angled brackets around 4, is that this command probably can have some other input, and this way it's making sure that this 4 is what dimensions are and not something else.
Again, so this just gives me leverage to define all kinds of matrices in any size. 4 is not all that useful, okay? But if I go to random, I could do this with 4020. It's going to be a mess printing things out, but I'm going to do it anyway. This is where I definitely don't want to print things. It's in there. All 40 by 20 are in there. It's hard to read, but it is defined, okay? And this is where these functions are powerful because they give me a very large array real quick. Okay. So let's do just a very quick and dirty plot before we head out. For this, we're going to use matplotlib. So I'm going to combine two things. I'm also going to tell MATLAB to import matplotlib. This second command is key. matplotlib.pyplot as PLT. So this is going to give us plotting variables. And very quickly, I'm going to give myself x's using np arange. And I have starting point 0. And then 2 times np.py. This is 2pi.
I found out the hard way. It doesn't identify arange if you spell it with one R.
Oh, is it 1?
I mean, yeah. So I tried it
Oops.
before. And I put 2 thinking.
You find out all kinds of errors as you go, yes. And I'm going to give ourselves a 0.05. But that's the best way to learn is when you find the hard way. Now you're not going to forget it. And I'm going to put y as simply sine function of this entire array. And I just want to plot it. Just give me 30 seconds to finish this. So this is my data, x's, and corresponding y's. I have the same number of each. And now I'm plotting it in 2D. Basic command is plot, and it's defined within this module. So I just have to import it. And then I just plot xy. When I do this, all it's going to do is going to set up defaults for me. Whoops, name error. There we go. Is this what you were trying to tell me? So I had a typo in there?
No, I think you got sign
Let's just make it sure. Ah, that one. There we go. All right. So now you got your sine function with whatever default parameters to do a plot. Okay? We're going to continue next time.